let's talk now about bond enthalpies, heat of vaporization, and heat of fusion. When we were doing Chapter 8, that whole chapter on Vesper and molecular geometries, we mentioned that single bonds were weaker than triple bonds. Not all single bonds are actually take the same amount of energy to break. So you can actually take a compound with a carbon-carbon single bond and break it and measure how much energy it's released in a calorimeter. And you'll notice that a carbon-carbon single bond might take 347 kilojoules per mole to break, but a carbon-oxygen double bond actually takes a little bit more energy to break, 358 kilojoules per mole, because you have a more electronegative atom on the other side of that bond than in the CC bond. All right, well, we can use these bond enthalpies to calculate how much energy is released in a reaction, just as well as we can use heats of formation. So down at the bottom of the screen, we have a problem like what's in your book. And in the problem, what they're giving you is two reactants and showing that when these two things come together, they form this particular product. Well, in order to calculate how much energy is released in this reaction, what you can use the formula that's shown on the screen, where you take the sum of the bonds broken and you subtract from it the sum of the bonds formed. All right, so if you look here, what you have to do is try to figure out which bonds are being broken and which ones are being formed. So if you look on the CC double bond on the compound on the left, that's no longer present in the product, so that's broken. And then you might notice that in the second compound, that hydrogen peroxide, it's that oxygen in the middle, those two oxygens that have to break, and so you end up creating two hydroxyl groups that can be attached on either side of the carbons in the first compound. All right, so those are the bonds broken. So you look up a CC, a carbon-carbon double bond value on the table. It's 614. You look up an oxygen-oxygen single bond value off the table. It's not on this table, but I looked it up on the internet. It's 51 kilojoules per mole. And you add those up, and that gives you the left part, what you would substitute in for the sum of the bonds broken. All right, so then you look at your final product and you realize, okay, well, you had to form a bond here between one hydroxyl and one carbon. You had to reform a single bond between carbons, and then you had to form another single bond between that oxygen and that carbon on the first reactant. You look in the table, how much does an OC bond, how much is that worth? It's 358 kilojoules per mole. How much is a CC single bond worth? That's 347 kilojoules per mole. How much is a CO single bond worth? It's worth 358 kilojoules per mole. You add those up, and if you want to figure out how the enthalpy of this reaction, you just again do the sum of the bonds broken and you subtract from that the sum of the bonds formed. Okay, let's talk now about heat of vaporization and heat of fusion. So this graph that you see here should be familiar to you. This is a heating curve for water. And I know it's water because I have a plateau at 0 and a plateau at 100. All right, so between -50 and 0, this substance is ice. It's in the solid form. Between 0 and 100, it's in the liquid form. At 100 to 200, it is now steam. And what we really should have on the x-axis of these energy diagrams is heat added. All right. Okay, so the plateaus here, the first plateau and the second plateau, this first plateau represents your enthalpy of fusion. So the enthalpy of fusion is how much energy it takes to melt ice, all right? And the value is 333 joules per gram. So it takes 333 joules of energy to melt a piece of ice. So remember, when you're melting ice, what you're doing with that energy is you're breaking the intermolecular forces between those solid ice particles and allowing those particles to expand away from one another so they can start moving faster again. All right, you notice in the plateau, the second plateau at the top, it's actually very long in comparison to the first plateau. The heat of vaporization is 2,256 joules per gram, so it's almost 7 times larger than the heat of fusion. And what the heat of vaporization represents is how much energy you have to add to water to break the last existing intermolecular forces that will then allow it to turn to steam. All right, you'll notice that it's 7 times greater, and it has to do with water. This is kind of a unique feature of water, because water actually is capable of forming more intermolecular forces than solid ice. Remember, with hydrogen bonds in a piece of ice, they form hexagonal structures, and that limits the amount of intermolecular forces or hydrogen bonds that can form. All right? So the heat of fusion is the energy necessary to get through that part of the plateau. The heat of vaporization is the energy necessary to get through that part of the plateau. All right? Now, There are some other numbers that I have on this picture. So we have this bracket down here at the bottom. This is the specific heat of ice. The specific heat of ice is 2.06 joules per gram Kelvin. This portion here in the middle is the specific heat of water, which is 4.18 joules per gram Kelvin. And this up here is the specific heat of steam, which is 1.92 joules per gram Kelvin. What the specific heat represents is the amount of energy that you need to add to either ice, water, or steam to get those particles to move faster. And the amount of energy that you have to add to ice is going to be different than the amount of energy that you have to add to water. And that's different than the amount that you have to add to steam, again, because of those intermolecular forces. All right? And it's the amount of energy that you have to add to raise 1 gram of ice 1 degree Celsius or 1 Kelvin. So you would need to add 2.06 joules for every 1 gram to get 1 gram of ice to go up by 1 degree. All right. For water, what that represents is that you would need 4.18 joules to raise 1 gram of water up by 1 degree. And for steam, it's 1.92 joules to raise 1 gram 1 degree. All right. So the question that you're going to have to do in your homework is something similar to the following. It says calculate the quantity of heat involved in each step shown in figure 6.11 and the total quantity of heat required to convert 500 grams of ice at negative 50 degrees to steam at 200 degrees. And they go ahead and tell you that the heat of fusion of water is 333 joules per gram. The heat of vaporization is 2,256 joules per gram. The specific heat capacity of steam is 1.92 joules per gram. And there's some numbers missing. That's why I gave you the prior picture with all the numbers for each part of the graph. All right, so what you basically have to do is you have to figure out, well, how much, and sometimes your book might ask, what's the total amount of energy necessary to take ice, 500 grams of ice from negative 50 to 200? And if that's the case, they want to know how much energy it takes to go through the entire graph. And I've kind of split this up for you segment by segment. All right, so first of all, if I want to figure out how much energy it takes to go from negative 50 to 100 to get me through this part of the curve, you're going to use that Q equals MCAT formula. All right. So Q is equal to the mass of water that you are heating up, times the specific heat of ice, times the change in temperature, so final minus initial. So we're going to end up at 0 degrees, but we started at negative 50. All right. That's how much energy it takes to get through this part. All right. How much energy does it take to get through this part? Well, the amount of energy there is going to be 333 joules per gram times the number of grams that you were heating up, 500. So to use the heat of vaporization or the heat of fusion, you just have to take that value and multiply it by the mass of substance that you're heating up. All right. Now, if we want to figure out how much energy it takes to get through this portion of the graph, again, you're going to use the formula Q equals MCAT. You take the mass of water times the specific heat of water times the change in temperature. If I want to figure out how much energy it takes to get through this plateau, this second plateau, it's just going to be the heat of vaporization times the mass, so 2,256 joules per gram times 500 grams. And then if I want to figure out how much energy it takes to get through this final portion, again, I'm going to use Q equals MCAT again. We have 500 grams of water. The specific heat at that point is 1.92, and the change in temperature is, oh, that's a mistake. It shouldn't be 0 to negative 50. It should really be, let's see here. It should be 200 minus 100. Okay, so that's a mess up here in this top part of this, right here. This should be 200 minus 100. I'm sorry, I made a mistake. So if they ask for the amount of energy to get through the whole process, you calculate the Q for each segment of this graph, and then you add all your Q's together, and that's how much energy it takes to go from negative 50 to 200. All right, so that should basically do it for today. Go and do the problems out of the book. If you have any questions, come bring them to me tomorrow.